How Tesla reinvented the electric motor. One of history's greatest inventors, Nikola Tesla, is well known for creating the AC induction motor. Modern inventors like Elon Musk began incorporating these AC induction motors into electric vehicles at the beginning of the 21st century, and this is how Tesla Motors was founded. Throughout the years, Elon Musk's Tesla has made continuous improvements to that original design, starting with the Model S and continuing with the Model 3 and their upcoming, unreleased next-generation electric vehicle. Tesla has reimagined the electric motor in this way. AC induction. First things first. In the grand scheme of things, the induction motor can be traced back to the early days of the Industrial Revolution, but the AC induction motor is a product that dates back to the early days of Tesla Motors and the construction of their first Roadster vehicle. Everyday electricity originates from outlets in your walls and travels through power lines all over your street. This type of electricity is known as alternating current. Around the turn of the 20th century, Nikola Tesla had a crucial role in the adoption of alternating current AC as the power source for the US electrical system. He is regarded as the father of alternating current energy. The alternating current induction motor, which essentially converts AC electricity into mechanical motion, and when used in the opposite direction, can convert motion into electricity, is widely regarded as Tesla's greatest invention. One of the first significant uses of Tesla's AC generator was the capture of hydroelectricity at Niagara Falls. The term alternating current refers to the direction in which electricity flows through a circuit. Therefore, for AC electricity to function, the electric current must constantly alternate between moving forward and backward. This can be challenging to understand in the context of our electrical grid, where electricity appears to flow from the generating station into our home, but is constantly moving back and forth. This feature makes it possible to send AC electricity across very long distances at high voltages, and then transform it into a lower voltage before delivering it to the customer. In North America, the direction of electricity alternates 60 times per second, yet the flow is so quick that we only notice it as a constant. In what way do electric motors fit into this? Magnets are the main component. Therefore, an electromagnet is created when electricity is transmitted via a conductive material, such as copper wire. The magnetic field also dissipates when the energy flow is stopped. Now, when you transfer electricity through a conductor in one direction, you create a magnetic pole, which can be either north or south. If you then reverse the flow of electricity through that same conductor, the magnetic field's polarity would also reverse. As a result, the electromagnet's north and south poles alternate along with the direction of electricity. The rotor and stator are the two fundamental parts of an electric motor. It's simple to remember which one rotates while the stator stays motionless. As the name implies, an induction motor induces rotational force in the rotor by use of a revolving magnetic field in the stator. This is how it works. Your stator is a ring of copper wire wound into coils that run from the front to the back of the motor. Each coil is wrapped around an iron object. When electricity flows through the wire coil, it becomes a strong electromagnet. Each magnet's polarity is determined by the direction of current. Therefore, by flipping each polarity in turn and alternating the directions in which the electrical charge is applied to the next winding, we generate a rotating magnetic field that travels around the stator ring. The rate at which you may alternate the flow of electricity can then be used to adjust the rotational speed of the magnetic field. In this instance, the rotor is a far simpler component. Different types of rotors are used in different induction motor designs, but the one we'll be focusing on today is called a squirrel cage rotor because of its structure, which consists of an aluminum bar cylinder that runs from the front to the back with circular metal end caps. The rotor is essentially just a metal cage that can rotate freely. It doesn't have any natural magnets or an electricity supply, but the stator's moving magnetic field can turn the rotor into a magnet. One of the fascinating things about magnets is that they can form an electromagnet simply by moving relative to a conductive substance and inducing an electrical current into it. This process doesn't require contact, just relative motion. If you drop a magnet straight down a copper pipe, you can observe this in action. The magnet will create a magnetic field as it falls, which will resist the magnet and slow its descent through the tube. The farther the magnet falls, the slower it will travel through the air because of the resistance caused by the induced magnetic field in the copper pipe. The same concept operates inside the induction motor. By using electromagnets and alternating current to rotate the magnetic field around the stator, a magnetic field is created in the squirrel cage rotor's bars. This magnetic field reacts against the stator's magnetism, which causes the rotor to turn in the direction of the stator's magnetic field, because magnets of the same polarity push against one another. As a result, the magnetic field rotates and the rotor moves quicker due to the magnetic push effect the faster you alternate the current flowing through the stator. The only thing to keep in mind is that the rotor must spin more slowly than the stator's rotating field because relative motion creates the magnetic field. If the two are spinning simultaneously, this motion ceases to exist, and the rotor will demagnetize and slow down. Since Nikola Tesla first received a patent for this type of induction motor in 1888, AC motors have been a mainstay of industrial society. They can be found in everything from ceiling fans and washing machines to elevators and streetcars. An AC induction motor is almost always found inside anything that spins and plugs into the electrical grid. Thus, the AC induction motor was a very clear choice for Elon Musk and the other founding members of Tesla Motors when it came time to select a power source for their first electric Roadster car. When utilized in an electric vehicle, this design offers you one very important advantage. We know that when the rotor is rotated faster than the stator, the rotor becomes electrified and produces a magnet. However, when the rotor is rotated faster than the stator, with the help of an external force, such as a wheel, the stator becomes electrified, which allows you to regeneratively brake, which returns excess energy to the battery pack. The Model S and Model X were built by Tesla using an AC induction motor as their main drive unit. This allowed the relatively large and heavy cars to accelerate to incredible speeds from a standing start, but it also had a major flaw that needed to be fixed. The next-gen electric motor from Tesla. Tesla was able to optimize power and efficiency in the motor design for the Model 3, but at price. When the original induction motor was released, it had an aluminum bar rotor that was basic and inexpensive. However, when Tesla switched to IPM's NRM, they were able to incorporate the rare earth element neodymium into their rotor, which means that in this case, the cost is money. The motor is expensive. Tesla is currently focusing its research and development efforts on a next-generation vehicle platform that will serve as the foundation for their next robot taxi vehicle. This platform is expected to maximize efficiency while drastically reducing costs. According to what we discovered at Tesla's Investor Day last year, the designers are largely cutting costs by removing rare earth materials from the motor's construction. Neodymium is not particularly rare in the Earth's composition overall. Rather, it is hard to detect at the surface and is rarely found in large concentrations in one location. As a result, prices are high and supply is limited. However, because neodymium has a powerful magnetic field that doesn't deteriorate with prolonged usage, engineers still favor it for electric motors, which helps to explain the expense. Currently, Tesla claims that their new magnets can function without any rare earth materials. What then will they use in its place? Ferrite is a widely used ceramic material that is primarily iron oxide, sometimes referred to as rust, mixed with additional metals including manganese, nickel, and zinc. However, it doesn't matter which one is used to make magnets. Ceramic ferrite magnets are used in electric guitars, speakers, cordless drills, and refrigerator doors. They also keep things closed, thus a very popular and reasonably priced material. The disadvantages of ferrite over neodymium are its lower magnetic strength. A far higher amount of ferrite would be required to equal a neodymium magnet's strength, and the limited amount of extra room within an electric motor. We are aware that Tesla can partially offset this by improving efficiency, as they have demonstrated in the past. Specifically, during the period between Model 3 and Model Y, they were able to decrease the quantity of rare earth material needed for the electric motor while maintaining power output. However, Tesla will inevitably see some performance loss in their next-generation vehicle as a result of moving to a ferrite magnet. For example, it may now take 8 or 9 seconds to travel from 0 to 60 instead of only 6. Does that mean the world is ending? Not at all. This is not a car meant for the racetrack, it is meant for mass transit. Since Nikola Tesla, good inventors have only sought to maximize the utility of the environment they live in. Specifically, they have sought to figure out how to accomplish more tasks with less energy. How can we blend several ideas to produce something fresh and more potent? And for the past 20 years, Tesla as a company has kept up this practice. Share in the comments. Please like this video, subscribe to our channel, and hit the notification bell to never miss an update. See you in the future video, and thanks for watching.